You know that popular superhero who can shrink and return back to normal on command while retaining all of his bodily functions, memories, and everything else? Correct, it's the Atom, Ray Palmer. Now, as much as it sounds like fiction, isn't it kinda insane computers can do the exact same thing, but with files? There are hundreds of compression algorithms out there, but they all fall into two major categories: lossless and lossy compression. Each one works well for different media and file types, so we're just going to take a look at a few simple ones from both categories and how they work. In order to understand compression, let's take a quick peek into what a file actually is. Take this image of Spider-Man. This image has a resolution of 3840 by 2160, meaning there are over 8.2 million pixels in this image. Let's take a look at just two of them. These two pixels are obviously different colors, but the computer doesn't know what a red, purple, or Becker purple actually is. That's up to the monitor and your eyes. What the computer does store are three numbers: one for the amount of red, blue, and green. RGB, which you've probably heard of if you're like a gamer or any sort of nerd. And the color space is very vast and can represent an infinite amount of color, but human eyes, monitors, and storage are a bit of a bottleneck. So we range all of these colors from 0 to 255. This 256 range might seem random, but it's actually the range of values that can be represented with 8 bits, called a byte, with 1 byte for each color space. This gives our pixel a total of over 16 million colors to be, and a color depth of 24 bits, which is the amount of bits needed to represent the color of a pixel. So, back to the bigger picture. Lossy compression takes all of that data and irreversibly throws some of it away. Sometimes it's the imperceivable data, like the difference between this red and this red. Sometimes it's inaudible frequencies in an audio file that we can't really hear because it's above 20,000 hertz or below 2 hertz. Other times the quality is very much perceived because you can't really decrease things like color depth and pixel count without it starting to get obvious, which is why these two images look similar but these two don't. A JPEG is a good example of a file format that uses lossy compression. There are times when the data stored in the file is necessary to the function of the file. Like a text file, we can't just throw away bits or lob some away because those are the individual characters that are being saved. If we did do lossy compression on the text, that would look like this, which is really no good. Which brings us to dictionary coding and Huffman encoding. These can be used together when storing text, but we'll try to understand it separately. In dictionary encoding, we find commonly used words or entire sentences in our text and give them a key that represents them. We can then substitute that key into the text, which will represent our compressed version. Take this poem, for example. We would make the phrase, "what the," be 1, and "'twas like a," 2. Then we store the text and the key and end up with, which means less bits for us to store. Fab job. We could very much keep going, making a key for every word. However, the usefulness of this is directly proportional to the amount of repeated words. Since we also need to store the key, if there are no repeated words, we would map every word to a unique key. And once we also store the key itself, we end up with more storage, which is not very good for compression. Next, we have Huffman encoding. Using our same poem, we sort all of the words by frequency, then build a tree. We take the bottom 2 items, add them to our tree, then their parent becomes the sum of those 2 nodes. We then resort the frequency list using this new sum instead of these individual nodes, rinse and repeat, and we end up with this graph, with the most common words appearing at the top and the least at the bottom. Now, every time we encounter, for example, a 1, we can move right. A 0, we can move left. We can then repeat this until we get a node with no children, and that is a letter. Pretty top notch. Finally, we have run length encoding. Instead of storing the same thing over and over and over again, like in a repeated string or an image with repeating colors, after some extreme details have been removed, we just store what it is and how many times it repeats. If a file has an image with 100 red pixels in a row, we don't have to save those pixels individually. We say something like red times 100. When the file is opened, the computer just expands it all back out. All of these compression methods are mixed and matched, and to be honest, this is really the tip of the iceberg when it comes to compression algorithms. I've linked a video of Tom Scott's that's really helpful explaining Huffman encoding. Anyways, thanks for watching. Bye.